So welcome to Systemd Part 2. This is supposed to be like the advanced part of Systemd. It's advanced in the sense that like everything that we saw yesterday, you will probably encounter in some way or another in the outside world or in the open wilderness. Today, you're going to see more a little bit of how Systemd works internally. We have Okay, so yesterday we didn't really touch on C groups, so we're gonna do a deep dive into, or a dive into C groups and how they're used with Systemd. We did told you that Systemd for each unit that you start create a C group, and that's how it keeps track of stuff. But now we're gonna use C groups as C groups, right? So to implement controls. Then we're gonna deviate a little bit and talk about Systemd for developers, right? So if you are a developer or you write code, how can you interact with Systemd in a way that is not just shelling out to systemctl and reading stuff? Or even better, how can you incorporate Systemd into your programs to make them, to take advantage of the fact that they're running on Linux? We're also going to talk about Notify. Remember that we talked yesterday a little bit about Notify. We're going to go a little bit deep down of what the hell can you do with Notify. Watchdog, somebody asked about Watchdog, so we're going to talk about Watchdog. And then Sandboxing, which is the cousin of C groups, which is sandboxing. And then we probably will have time, but if we have time, we will talk about eBPF, maybe socket activation, if that's, or maybe we can finish the Systemd analyze of last time. So that's the walkthrough for today. Are you excited? Thank you. Okay, so Anita, do you want to start? Yes, that's the word.
Okay, so hopefully everyone has the table of contents open. Mirror? Oh, I didn't mirror. Got it. Display. Okay. Okay, so if you have the table of contents open, we're just going to go into Systemd 201 and click on the C groups link. So we're not gonna dive super deep into C groups, but we're gonna get some of the essentials out of the way since we didn't talk about it yesterday. This really gets into how is Systemd implemented. That's kind of the goal of what the C groups module is gonna talk about. So what are C groups? C groups are a kernel feature, and it allows you to manage, restrict, and audit basically groups of processes. It's pretty much one of the fundamental features of modern day Linux, and it's essential for any containerization that you do. And of course, it's kind of the backbone of how Systemd organizes its units. Pretty much the majority of units in Systemd have an associated C group with it. Definitely services, which we talked about yesterday, scopes, and today we'll also talk about the slice type. For the purpose of the workshop, we're only going to be talking about C groups 2. In newer versions of Systemd, we're starting to phase out C groups 1, so I don't think it's going to be super relevant if we go over it here. So what exactly is C groups 2? It's just a virtual file system mounted at sysfs C group. It's basically a tree of files, and we can start by making a C group of our own just to see what's in it. So go ahead and make a directory under sysfsc group. And we are going to ls. See what's under there. You'll see there are a bunch of C group related files, files related to CPU, I/O, and memory. So the CPU, I/O, and memory files allow you to control the knobs for resource control. And they're examples of controllers that you can actually enable or disable for the purposes of resource control. So how do you know which controller is actually enabled on a C group? You examine the cgroup.controllers file. So for us, we just ls the, well, actually, I wrote ls, but I meant to say you want to cat the C group controllers file under the C group that we just created. And you'll see that right now we have the CPU, memory, and PIDs controller enabled. So let's run another quick experiment. We can create another directory under this unit that the C group that we just made using the make dir command. And we're going to call it another foreign unit. And we can examine this one with ls. And you'll notice that there are actually fewer files here than in the first C group that we created. So why is that? So if you peek into C group controllers for the nested C group that we just made, you'll see that there are no controllers enabled. So if you have nothing enabled, you don't have any of the files you'd use to tweak resource control. So how do you actually enable and disable the controllers on a C group? You actually go back to the parent C group, and there'll be another file called cgroup.subtreecontrol. If we cat the one for the parent C group, you'll see that it's empty, and that makes sense because we don't have anything enabled in the child C group. So how do we actually enable it? Well, you just echo the name of the resource you want into C group control or subtree control, and that will enable it in the child. So I have the commands right there, echo plus memory string into the subtree control. And now if we check the file, the subtree control file again, we see that it's there. And if we go up, we can also check the child's C group controllers, and you'll see that memory is enabled. And if we go back in history a couple more times where we actually ls the child C group, we'll see that we now have all the memory files. Are there any questions about that so far? Hopefully that was straightforward so far. So now we get into how does systemd use C groups? Well, so actually writing directly into the C groups tree is a violation of one of the contracts that we have with systemd. The idea behind like C groups 2 is that there's really only one writer to the C groups tree. And systemd is that writer that is going to be mostly modifying the C groups. And we kind of want that because systemd will, as you saw in the example, it will need to continue enable and disable controllers as it creates new units. And if you're also writing to the C group controller or the subtree control at the same time, you could run into some pretty bizarre race conditions, or you fail to enable certain controllers, or you won't be able to set up your resource control management successfully. So mainly we want to avoid conflicting with what systemd is doing when it's creating C groups. However, systemd does let you control certain C groups with the delegate property. And what that does is it tells systemd that you want to manage this point of the C group downwards. And before we do that, we also tell systemd which controllers we actually want to enable at the same time. So we can actually try this out with the systemd run command. It'll create an ephemeral unit for us, and it'll tell systemd to delegate it. Oh, gosh. Oh. So what this systemd run command is doing is that we're going to create a service named myFirstCgroup. It's going to set delegate to yes, and then it'll exec into sleep infinity. Delegate equals yes. So in addition to telling systemd that we are going to manage the C groups from that point on, it will also enable all of the controllers that it can.
Keep going. I'm just going to fix some things.
So now we have a myFirstCgroup service, and as usual, we can get a little bit of info about it. And if you cat it, you can also see that we have this delegate equals yes under the service part of the unit file. Let's see. So if you check systemctl status, you'll see that there is a C group field there. And for brevity, systemd usually omits the /sys/fs/C group part. We just assume that that's the root C group, and I'll probably be saying like root slice or root C group from this point on. So if you wanted to examine the contents of myFirstCgroup.service, we can just go ahead and copy the C group name. And you'll see that systemd has created this unit for us with all of the resource control files available. We can also double check this by examining the contents of the C group controller file for this unit. And you'll see that we have CPU set, CPU, IO, memory, and PIDs controllers. Now we're going to do what we did before and create another C group under the one that we just created for myFirstCgroup.service. So I'm just going to copy the command, and this new C group that we're making under is called pew pew. So one thing to notice here is that systemd doesn't stop you from creating C groups. Like in the previous examples, we were able to write to the root C group. Nothing's really stopping you from doing that. And in this case as well, it's not going to stop you. However, there is a rule in C groups too that you can only have processes in the leaf C group nodes. And if you don't, then the kernel basically prevents you from doing certain actions. Like for example, if we try now to enable the memory controller on for pew pew by writing to the subtree control file in myFirstCgroup, it won't let us. So we can give that a try right now. And you'll likely get a device or resource busy error. It's a little cryptic, but as long as you remember that you can't have processes in like the middle of the C group, it has to be on the leaf node, basically where you have no children C groups. That's pretty much what's going on with this example. And you can verify that there are processes in myFirstCgroup by catting the cgroup.prox file. Or if we run systemctl status again, you'll, like before, then you'll notice that, yes, we have a process under the C group. Okay. So the question was, is the rule that you can't modify the C group after you create a child? So yeah, I mean, you can continue to create empty C groups, but you can't do anything with them, so to speak, until you actually move the process into the leaf node, which is, yeah. So we're about to do that, and then you can see that we can start doing stuff again. All right. So yeah, like I said, we can actually move the process from that parent C group into the pew C group by echoing. I'm going to take the PID that we saw and write it into cgroup.prox of pew. And now if we try to, if we check cgroup.prox, we'll see that there are no more processes under my first cgroup.service. If we check pew, we'll see that it's actually there instead. And now if you try to write to the subtree control file again for my first C group, it succeeds. And so we are able to successfully enable the memory controller on pew. Okay. Any questions about that example? Okay. So I kind of threw around the term resource control throughout these examples, but really it's just a fancy way to like control or define limits on certain resources like memory, I/O, and CPU. For example, how much memory a C group uses, how much CPU time a unit should get, things like that. I'm not going to go into like every single resource for this workshop, but I think it'd be fun to go into memory management since that's something that's, most people kind of can wrap their head around. So let's start by creating another service called sleepy service under a slice called tester. Sorry, I ran this morning, so I need to. Okay. Like the previous example, we're using sleep to keep the service up and running so that we can examine it. And one of the tools that we're going to use to watch the memory growth of the unit is systemd cgtop. So for this part, I advise using tmux to split your screen. And on the left side, I'm going to run systemd cgtop tester slice. And it's kind of squished here, but you can see that sleepy service is right here, and it shows that it's currently consuming about like 200K of memory. And this actually periodically updates as long as there are other units here to watch. Okay. And now we're going to make a second, we're going to make another service under tester.slice. And I have a quick question for everyone. What do you think this command does? The systemd run memory max equals 50, and then we're going to tail dev0. Any guesses? I saw a hand there.
Limits the process to half the available memory.
Limits the process to have the available memory.
That's actually a good guess, but it's getting there, but it's not exactly right. Does anyone want to make one more guess before give? Oh, over there, We have a contender. Ooh, even closer. The gentleman over there said that we'll use up to 50% of the available RAM, and then it'll start to slow down. So let's just run it, see what happens. So on the left, you see that wow, it went by really fast. But if you briefly saw what happened, the service appeared, it used up a bunch of memory, and then it disappeared. Let's check the status of this unit. You'll see that the service actually got killed. So if you briefly caught when it got killed, it was about when it was using 50%-ish of the RAM. So memory max is a hard limit. If your C group is using, in this case, 50% of the RAM, you're going to run up to the memory killer, the kernel killer. So that's basically what happened here. The gentleman who said the system would slow down, there is a throttling option for resource control. I believe it's memory high, but we're not going to go over that one today. If you check out the man page for systemd resource control, you can get an overview of all the different knobs that systemd allows you to control related to C groups. And then you can kind of pick and choose which ones are necessary for what you're doing. Any questions about that? Okay, so moving on to slices. I created a slice in the previous example, but you may be wondering what the heck is a slice? So similar to target units, which allow you to synchronize different units and group them together for the purposes of ordering and dependencies, slices basically exist to allow you to organize units for the purpose of resource control. So if you want to, if you're asking like, well, how do I organize slices? Like what kind of grouping are you talking about? You can kind of check out systemd slices for an example. So systemd has a tool called systemd-cgls. If you run it without any arguments, it's basically the equivalent of running it with the root C group. So it's going to show you a kind of tree-ish like structure of all of the different units and all the C groups basically that have processes running under them. So if you scroll down a bit, you can actually see where from the first example, we created my first C group service, and we have the pew subgroup, and also it still has sleep running since we didn't shut it down. So we have a pretty basic system here. Then there's really only, well, 3-ish C groups if we consider the one we made for the test. There's user slice, which is the slice that systemd uses to organize all of the user-related processes. So when you log in as non-root, it'll start up a user manager. Those spawn further C groups and things like that. Those all go under user slice and are further grouped up depending on what the user ID is. System slice is the one we've been working with the most. That is basically the default slice for units that you make with PID1. And that's all we have for this one. If you look under, if you have like a Linux machine and you are running GNOME or KDE or something, you'll see that there are even more slices related to applications or background processes and things like that. So I guess a quick audience poll. What do you think are some real life examples where you might use slices? Yes.
You have a shared infrastructure and you want to slice per team to monitor resources.
Oh, yeah. So one way you might use it, as this gentleman said, is that if you have a shared infrastructure and you have per team services, you might want to use slices to split them up by resource allocation per team. Any other examples or guesses?
What about sharded databases where you need to have more than one instance?
Oh, interesting. Sharded databases.
So you're saying something like give to the main process or the leader more resources than the followers, or vice versa? You mean something like that?
Well, in some cases with Oracle or with Microsoft database server, because there's so many transactions, you need more than one, and it's distributed like a cluster.
Oh.
And they call it sharded.
That's interesting. So what the gentleman here is saying is that you could use this to, when you have a database that's certain chart of the database are more resource intensive, you can give them higher privilege to do stuff. And I guess you could do it as long as you can traverse the process, as long as you can like redirect all the rights to a certain process, you could use that for that.
The
Yeah.
idea is when there's a database that has so much transactions, you distribute it so it's in parallel.
Yeah.
Yeah.
Yeah, but this has to be on the process layer, right? So it's you send if you send a query that you want to process to the main process, the thing that has to process that query has to be a different process. So it could have a different C group, I think. Okay. Yeah. The other one that you can do is that when you want to have lower level things on your machine, like Chef, you want to give it less priorities than, for instance, like your web server.
Yeah, I think we covered some pretty good examples, especially Alvaro kind of hinted at how we kind of do it within Meta, where we split out like the host critical services from the workload services and have different resource control constraints on them.
I do have one question for the audience. So, or for you, Anita. Everything, everything in systemd runs in a C group, right? So, sorry, everything in Linux runs in a C group, right? Yeah, and is what's the C group that systemd runs? Oh, or anybody, like how can we figure it out? Like, how can we figure out what's the actual C group that systemd runs? CGLS? Yes. So at least the way that I would do it, it's systemctl status 1. But it's both achieve the same process.
Cool, and that's the end of our C groups explanation. And now Alvaro's going to talk to us about systemd for developers.
Yes?
That last command you had, why did you put the 1 after the system?
Oh, so the systemctl status allows you to specify either a PYD, a PID, or a unit, right? And systemd runs as, it's the first process that runs, so it gets the privilege to be called PID1. So if you do systemctl status 2, you will get the second process that run in your machine. That probably doesn't exist.
What if you just put status with no number?
Oh, that's actually quite cool. You can do it. You see a tree of everything that is running, right? Not everything that has run. Okay, so we could take a 5-minute break. And as is usual, provided by our good friend Nish, we have Portos at the front. So if you want to get some pastries, go for it. Also, use this time to stretch your legs or whatever you need to do. Okay, so we're gonna start in a minute. Well, give time for people to sit. Okay, so the reason why we do these stops and rests is because it's important for people to take a rest, they eat, go to the restroom, stretch, because sometimes we get long topics, and this is one of those. So, but at least it's a really fun one. What we're going to talk about now is systemd for developers, which is not the same as if you're a developer and you want to develop on systemd. This is mostly like if you're a developer and you wanted to interact with systemd or use systemd at your advantage. So the same as the group, we need to go through a couple of basics. Who here is familiar with dbus? Okay, great. That's good. Like at least you know that it exists. That's good enough. So dbus, it's very controversial, but in general, it's an IPC service that runs on your machine that allows different processes to communicate to each other, right? So in general, it's a nice way for a service, aka let's call it GNOME, to have an interface for people to, or services to interact with it, either like get information out of it or ask it to do things. It's basically an RPC. The reason why I mentioned this is because systemd used this a lot to communicate between different parts of the service, right? So when you're doing systemctl commands, what you're actually doing under the hood, or most of the time, you're calling to a dbus interface and talking to systemd daemon. And then you're getting that information and displaying in a nice fashion. The good thing about that is that it doesn't have to be systemctl the one who does that. It can be your own program. So, for instance, like in the old days, when you're writing your batch script and you wanted to know if the process was running, you usually write a command, and then this thing would write a text output to stdout that says like running, and then you need to parse it with some grep or anything to get that information. With dbus, you get that information for free. If it is a Boolean, you actually get a real Boolean value. If it's an integer, you don't need to do like parse int or anything like that. You just get an integer. So with that introduction, let's get into it, right? So the best way to start using dbus, it's let's inspect the bus, right? So let's join, connect to a terminal, and then just run busctl. And then you get an output that is kind of like this, right? So you're gonna see a few things. You're gonna see a few numbers there, PYD, process, user, and a bunch of those things. So these things over here are called services. And you see that they follow kind of like the DNS type of fashion, right? So the services have names, and this can be like numbers, and this would be like IPs. And then they can also have a name that is actually like a dotted hierarchy, and that is kind of like DNS if you want to sync it. And a lot of the times, processes can have numbers and names, right? But here you're going to see that, yes, there's two things here, right? So what is a service? So we can go and do busctl tree and then put one of those services there, in this case, we're going to do systemd. And you're going to see that this comes as a tree. And it's very interesting because now you see it says org, or free desktop, log control, systemd1. Clearly, this is where the tree died. Then there are jobs. What are jobs? We don't know. We will see later. And then we see units, right? And then we see things here that looks familiar-ish. right? So like if you squint, you can see that this says Divas broker service with this weird 2_2e. That seems to be an encoding version of a dot, right? So these things over here are the instances. So you can see a lot of structures, and you can see that if we started my service, let me go here. If I remember from our first day, I think we can start my service. You see that it appeared there, right? So this is how you know what things are running in your machine, right? Like we will do this programmatically later, but in general, you can see that, okay, so I just need to know that there is a thing called or free desktop to systemd1, that you actually saw it from just looking at the first output. You see, oh yeah, there is a bunch of this, right? And then when you see the tree, you will see that the service has started, right? So we have service, we have the object or the instance. I don't know what name I put it here, but yeah. So now let's see the actual object. So we don't want to see the tree. We want to inspect. So did I write that well? Introspect, not inspect. English, what a language. Okay, so very simple. You can see we specify the service, then we specify the lift or the object, and then you hit that, and then you see that it shows you a bunch of things. It shows you some interfaces here. And by the way, the reason why I'm doing this, I'm trying to show you like from nothing, how can you like start like exploring this, or how I discovered Divas at least. So you have this thing that is called introspectable, and here that's kind of like the interface, and it says tester interface, and it has a method that is called inspect, right? Then there is a Divas peer, this has two things, and then there's a properties, perfect, and then you can see that all of this is like Divas namespace. But here's where things start getting interesting. There is an org free desktop systemd.service, and here are a bunch of methods, and then there are properties, and then BuzzCTL is nice, and it shows me, oh yeah, and it shows me kind of like the value of those properties. But you can see that things from yesterday, things that you would set, like the CPU weight is already set. It kind of tells you the property, sorry, the type in a type system. It's kind of showing to you that there's such thing as integers, but there's also such thing as arrays. You can see that remember that when we start, we set an environmental variable, but we set the environmental field, so you can see that that's the value that it has. So if you want to know what environmental variables was set at the beginning, you can just like call those. And very fun. But this is where I wanted to go. We will get there. There you go. And now you have another interface that is called systemd1 unit. So you have a service, which is part of the runtime, and you have the unit, which is part of the definitions that you actually put into your document. There's not really like you can see that these things don't actually namespace collide. The concept of the interface is there to avoid collisions, but it's also kind of a logical grouping. So you can see that there's a method that is called start, and there's a method that is called stop. So like systemctl start under the hood will call a Divas method on this interface, right? So before I kind of go a little bit further into this, any questions so far? Go ahead. Oh, that's a good question, and the answer is I have no idea. So the question was, will there ever be a systemd2? And don't know. I don't think. I actually don't even know like why is the convention to put a 1 at the end. But yeah, sorry, I don't know. But that's a good question. Go ahead.
When you started this session at the beginning, you said this is controversial. What do you mean by that?
Oh, so the question was when I started this section, I said that divas is controversial. This is like a very nerdy topic, but some people don't like divas, especially back in the days because it wasn't very reliable. Let me put it like this: if the demon is a if divas demon, which is a demon running on your machine, hangs, like your machine is dead, right? Like there's basically not much that you can do about it more than reboot. Yes, and reboot doesn't use divas, or doesn't have to use divas. But yeah, it was very unreliable. There was very competing like implementations for it. But I think over the years, like divas has become very stable. I know for certain that we have steps where we needed to reboot like fleet, not the fleet, but section of the fleet because divas, we did a wrong update or something like that. Anything to say about that? Okay, go.
If there is a reboot, do you have to do extra steps to get the debus back up?
No, in theory, the thing is that like if you debus or anything that you just need to reboot your machine so that when it starts, brings it up, right? If debus is screwing away where it cannot start, that's a very hard thing to recover from. But that's almost like saying like systemd cannot start. Go ahead. So you're saying that Divas was doing a lot of syscalls? That was? Okay, yeah. Yes. So I think what you're saying is that like Divas was very chatty, so there was a lot of messages on the bus, and there definitely are, and we're going to see them. But yeah, you can definitely abuse this. This is IPC for processes to talk to each other, not to run a chat server, so please don't do that. But yeah, okay, cool. So since we're learning about Divas, it's nice to actually see a little bit of of how this actually came to work. So every single Divas interface should implement at least 2, if not 3 interfaces, right? So if you are building your own Divas server, you should implement the introspectable, right? So that way, if you see, if I do passctl introspect, what this is doing is just calling the method introspect on that interface. We're going to do that in a second. But the other ones that you want to do is you want to be able to read properties more than one at a time, so you get all you can set. And then, and I didn't talk about signals. Signals are things that you can hook yourself, and Divas will like show you like this happened, right? So you can like read the Divas, hook yourself to that signal, and then when a property change, do something, right? This is how you can kind of like proactively monitor when your services are down. As soon as they're down, there is a message on the Divas that you can hook yourself and say like, hey, like call the cops. I don't know. And then there is this one, the peer, which is interesting. These are just like to test functionality. So let's go here and let's call get property, right? So there is a passctl allows you to get a property. So you can do so you can do passctl get property, then the service, the object, the interface, and then the property, and then you call it, and then it will give you the answer back, right? So that's how you know. We can check with systemctl status. I'm going to do a reverse idea and actually like check by PID, even though I could check by the service name. Actually, since I have my first competition, I should be able, you see that it's giving you the information that you want. So that's the get property. And what this is doing under the hood, it's calling that one single interface that you already saw that is called get from the properties, right? So under the hood, this is just doing that. So yeah, so without further ado, let's do that in that sense. So the thing with call is that, right. So I do call the same thing. I give the service, the object, the interface, the method, but then if you see get takes two parameters, which are SS, which mean string. So the first parameter that it takes, SS, is the service name, and then the other one, sorry, the interface name, and the other one is the PID. And you can see that from my get property literally passes those two parameters directly, right? You don't need to specify those because that's a convention. It should take those two things. And then you see this return the same thing with this V at the beginning, V, that is called a variable type. So the next element after the variable type is the actual type. It's whoever deals with type systems seems that this is very familiar, but yeah, that's the one. So we kind of like know how to do this, but we can do other stuff like restart. So we remember there was a method that was start, stop, restart, and you can do the same thing with systemctl. This you can call it directly without having to go through systemctl. Replace, so restart. Actually, inspect. Sorry, introspect. Perfect. And then let me do. You see, restart is a method over there, and it takes an S. So if I were to call this method over here, you see that I pass the name, the S, and then I pass an argument after it. And to go ahead.
Sorry, I have a question about the interface. How do we know, so we already know the service name, we know the object path. How do we know which interface?
Okay, cool. So the question was, how do you know which interface the objects wants to, or the call wants to? Yes, exactly. So when you did your introspect, this is tree-based, right? So you have, you see that it says like org, everything that is under it belongs to that. And it's in bold, so you know that that is important. Actually, like this is how like you know by looking at this. But if we do, oh, this is going to be horrible. I do think I have I do have an example further down the line. Yes, this is the one. So you know that there is a single you know that there is the interface for introspect and the method for introspect. That's something that you know it exists. It's there. So you can call it and then see the output, and then it gives you an XML because why not? But yeah, so you can do XQ, and then you will see like here the XML has like this tree structure where you can actually inspect it from your program, from the point of view of your program, right? So here you will see that eventually I will find the interface. Yeah, that's it. So the interface, and here are the method that belongs to the interface. So you can like programmatically search this, and we're working towards that point. So don't worry. I'm not going to force people to do vastctl commands all their life. You're welcome. Where were we? Oh yeah, the restart. So the restart, it's very simple to take as and replace. And this is the only part where vastctl doesn't tell you what to do. It tells you what is the type of the thing that comes, but it doesn't tell you like information about the thing that is under it, right? So the parameters, some implementation of divas, parameters have names, so that then that can be more interesting, but in particular, the one that systemd uses doesn't have name parameters. So you kind of have to figure it out that restart takes one argument, and that argument can be replaced, and that's nice. What replace does, it is very simple. You're going to send a job and say, hey, can you please restart this service? And if there is another job that is running that is trying to restart the service, it's going to replace it. There's other options like ignore and all those. So you do it, and then you see that, hey, I have a job over there, right? And you could, in theory, inspect that job. But that job doesn't exist. Yes, but the job doesn't exist anymore. So we can do, I don't know if we can do, I hope we can do this. Then probably do an n of 0.2. Is that a thing that exists? Perfect. So go here. Let's see, this is all to see if we can actually, yeah. We don't even get a chance to see it. It goes so fast, but it will put it into the bus for the existence of the process. Okay. So this is what I was saying, right? So if you try to introspect that object, it says that it doesn't exist. But if we do, oh yes, I remember I did this. So if you try to do it like right there on the spot, you do get to inspect that object. So what I did here is that I call the unit, and then remember that this returned me the job. Then I grab that job and then introspect it right away. So as long as I'm doing like instantaneously, I can see it. And then you see a job, right? That is like there. You can cancel it, like get all this information out of it, and it's great. Okay. That's all I have to say about that. And if you want to believe me that I actually restart the thing, oh, yes. You can see that it says that it started like 37 ago, right? 37 seconds ago. So that's cool. I think we already talked about the common interfaces of divas. So the first one that I wanted to show is like was introspectable. That's the one that sounds very interesting. That's the one that we are gonna abuse to build our system, right? The next one here, okay, sorry. And that's all we have to say about that particular section of divas. Now, the gentleman over there says that divas was very chatty. So how do we know that divas is chatty or not? So how do you, like, one question here, like, how do you know if you are getting connections to your web server in your Linux laptop? Like if you don't know if it's working or not working, assuming that you cannot just curl into the endpoint. How do you check that? What are the calls, the network calls that are going on your machine? What tool would you use to check what is the traffic on your machine? TCP dump, journal CTL. I would use TCP dump. That sounds like a good idea. So, well, there is a thing called the CTL monitor, and this is quite cool. So this is great. It shouldn't, like, it's very chatty. Oh, shit, sorry. Damn it. The reason why is because I'm doing this here. So let me actually stop that, and yeah, that should be a little bit. Right, so if I do systemctl status, my first service, sorry, and I do here restart, you see that I did that, and these are all the divas messages that went through the divas hook, right? So this is what I say, like, that you can hook yourself to the divas event and then filter out or only subscribe to a certain type of event. And you can see that, let's see if there's anything here that is worth looking. Let me clean this up. Let's do this again. Okay, so you see that there is clearly a method call. That's not me. That's not me. Okay, so here it is. You can see like there is somebody calling system D1. This is the path. This is the interface. And somebody's getting a property, which is the ID of the unit. That's not me. And then somebody is getting a bunch of properties. There's a bunch of method calls. And yes, here it is. Somebody's getting the ID again, and it's doing all this process. So as you can see, somebody called a method. This is a return. They were getting the service name. So you get all this thing from the bus. Okay, so that's good. So we can do something maybe a little bit more T-Bus-y. So now the good thing is that somebody says like we can use TCP dump, right? And this is a network thing. So maybe we can do something similar. So there is a nice interface over here that you can use that is called T-Chart. So you can, instead of using monitor, you can say capture, and capture will send to std out a TCP dump-like format, right? Or TCP dump format. I think it's called pcap. I don't really know what is the name of the server. But then since this is a shell, we can use T-Chart to like get that data, and we can provide a filter, right? So there's not really that much things that you can do in Wireshark with the service that you have. Like not many filters that you can do, but this is one that seems very useful. I say DBus looks similar to the first service. Then I hit it, and then I think I need to restart. And then you see all the calls that are going through DBus that are related to that service, right? So you see property changes, which are signals, and then you see some introspect and some gets, right? And you see that there's one thing that says 1.2 to DBus, and then 1.44 to free desktop to system D1. When you're talking DBus, and it's the same way that when you talk to a web server, like the client has a port in your machine, right? That's how TCP works, right? You grab like a very high port, and then you tell server, send request to this, and vice versa. This is the same thing, right? So when you're talking in DBus, you need to grab a name. If there's no port, there's kind of like an address, but you get the idea. Yeah, and that's it. Nice. Okay. There you go. So oh yes, I remember why I did it. Now, I don't know if this is going to work, but I'm going to try it either way. What I'm going to do is instead of like pathing into T-Chart, I'm going to write it into a file. And I'm going to write opt-conf plural. Let's do restart, and then let's cancel it. And then if this works, and I have my code. Yep, code, and then we have my workshop, and then I have my conf, and then I have my sprawl that I created. I have my pickup over here. So if I do Wireshark, this is why I say I don't know if I have Wireshark installed. Why don't I? This is upgrade. I guess I'm just going to install it. Fedora, don't fail me. And we'll come back to this when this is installed. But yeah, but the point is that you can see this pickup in Wireshark. Scale Wi-Fi. Okay, let's move on. when that's back, we can check it out. So this is like the first layer of like we are learning and understanding how Divas works. Any questions so far? Go ahead.
Is that output very similar to what you get with S-trace?
Oh, yes, and sorry, the answer is no, right? When you get with S-trace checks syscalls, right? Syscalls are the interface between the kernel and the user. Where is it? Everything that happens in Divas, or sorry, most things that happen in Divas that are interesting happen in user space, right? Like, yeah, there's message passing and that you open connections and do all the stuff, but the actual content of the things are, or the interaction that happen, or the content of the introspect, it's just user space stuff. Yeah, so that's the one. Did this. It's gonna take. But yeah, as you can see for my bar over here, we have half an hour, and we are still a little bit less than half of the tutorial. But we're going to shift to a very fun part, or at least fun for me. So, systemd, it's instead of using, because why would systemd do this? Instead of using a standard library or something from the outside world, decided to rewrite the Divas libraries and bindings, right? So they created this library over here that is called SDBus. SD, of course, is systemd. Not an S and a Divas. And this is very interesting, right? So this is a library that it's like, this is not particular, like the library belongs to the systemd suite, but it's not just for systemd Divas, right? You can use this to build your own Divas server even, or interface. And you can use this to communicate to other Divas. So when I first saw it, I really liked the library. So I decided to create a Python binding for it because I have a necessity of creating Python binding for every C library that I see out there. So I created systemd, which now is part of the systemd project. Like originally was part of method, now it's part of systemd. Very proud of that accomplishment. But this is like nothing fancy. It's just Python bindings to talk to Divas. But this also means that you can do a lot of higher level stuff very easy, and then you can write tutorials that are very easy to follow. So I created a thing that is called systemd shell. So if you can and are willing, I recommend that you do systemd shell. And the first thing that you're going to notice is this beautiful ASCII art. Right? So that's the logo of systemd. That's over there is the logo of systemd.py. Right? Just as a question, the systemd logo, does anybody know what that is? Do you want to give it away, Anita?
It's the OK from when you're starting up your host.
So do you remember that when you start your host, there is a bunch of text going on, and then every time that something starts, it says OK in green, and if it's red, I don't remember, I think it says error. That's OK. Not in a million years would I figure that out. But it's cool. And we sell those at the exit. No, we don't. Okay. Okay, cool. So go ahead. Any questions? No, okay, cool. So systemd shell. This is just a Python shell that already comes with systemd install. You just pip install it. But in general, this is just for demonstration purposes. And it's pretty good to test interactive stuff. So you can do something like import systemd, even though it's already imported, but let's follow the tutorial. And then you can do the following thing, right? So remember that the unit has this weird 2E underscore. So you don't need to remember that. You can just encode a library. And then you can see that you can, oh shit, Sorry, damn it. Okay, so now you get your unit name there. And then you can ask for that object over there. So you can just copy that. And then you just load that object. And now you get something that is quite cool, that you can get service. And you can do tab competition here, and you get main PID, right? So now you can remember we came from a world where we were patching shell script to just having an object with all this data in it, right? Now, Python is not doing anything there. What it's happening there is that under the hood, when you did load, it went, inspect the object, read the XML, and then create the object based on the XML that give out, right? So now you have an object that looks like the object in Divas, but was created on the fly. So there's nothing hard-coded here. Now, when I call the main PID, knows there is a property, get the property from the Divas, and parse it as the Divas tell it to parse it, right? It tells it like this is a string, sorry, this is an integer, so it returns an integer, right? So there's no, like you cannot call this and this will return a hello world instead of like a number, and then you will get an exception. I see that I'm not that Sweetie doesn't like me that much. Okay, okay. So you get the load. You can also call this property. Remember that we have, and you also get that without all the fancy stuff. And like I was saying, you get this as a type integer, so like you can do programmatic stuff. Right. So that's how you can build. I built this in Python. You can build this in any language that you want. Go, Rust, go nuts. I do want to mention one thing here. Now we have Wireshark. Let's go back to the previous open workshops, conf, sprul, pickup. Oh yes, and now you see that here you get all sorry to bring you back to the topic, but this is, you see the pickup, and then you can do all the nice filters that you would do in Wireshark, right? The one thing that it doesn't have that is really cool that Wireshark has, but it's not really well implemented. You can say, for instance, in a TCP dump connection, you can say follow just this connection, and it will just show you all the connection. This is pretty cool when you're doing other protocols like voice over IP. It kind of shows you all the SIP messages. With Divas doesn't do that, but it's good enough, and you can do all the same filters like Divas path and all the stuff. Right. Okay, sorry. Now going back to this. So this is where the magic happened, right? So we get an SD object that reads, where you give the interface and then the path, and then it knows. But you need to call load in it. And there is a reason, there is a philosophical reason why you need to call load in it. And the philosophical reason is that you shouldn't, and I say like in my opinion, you shouldn't make network calls in object initialization, because that's an IO-bound call, and whoever's using your API may not be aware that you're doing that, so you may block like an event loop or anything like that. So you want to do network initialization or anything that does IO explicitly. So this is why I put a load there. With that said, if you don't care and you're smart, you can do this, an initialization, two ways. The first one is that you can do the same call, but just pass autoload through. If you do that, then you just get the object for free, or you can do the Pythonic way, which is you say with. and you do st object service dot main feed. Does that work? Yeah, but I need to do a print so you can see. So so you can also like use the context manager, and it knows. And it knows that also it needs to close the connection after it. Oh yeah, and there's the context manager, right? So, good. Let's go here to the auto load. The thing is that these two ways of doing it with the context manager or with the extra options are explicit ways that you are doing this, right? So you cannot like accidentally trigger a network call like this. You know what you're doing. So I already mentioned that there's two interfaces, service and unit. These are where things exist. There is also properties. And you can inspect the interfaces by just inspecting the interface underscore, right? So again, this is built all under the hood for you. All right. So far, so good? Okay, go. The next one it is that since this is systemd, you can take some liberties and kind of like you don't need to force the user to tell you all the information. So we know that there's a very important thing in systemd that are called systemd units, right? That's the fundamental thing. So we don't need to go through this divas object or SD divas or whatever it's called. We can just go and have an object. And, and here's very simple, right? Since it's a systemd object, we can just pass the service name, and we don't even need to encode it. That's kind of like the idea, right? So we know that it exists and it's there. And we can restart it. And it gives me the object at the end, right? So this is kind of like very nice to do. This is, okay, cool. We did with the units. There is another type of interface that we haven't seen today, but it's the manager. So like you can talk to the unit and say, stop this unit. But what if you want to start or stop multiple units, like, like in Anita's dependency tutorial yesterday, right? So for do that, you need to talk to the manager instance. So you talk to this beautiful, yes, Anita, who is the manager. Yes. And then you see that the manager has a manager interface, and it has a start. Well, it has the start transient unit, but it start units. So you can call all of these properties there. One thing that is very interesting is that you can actually get the unit by PYD. This is like, remember that functionality where we were saying like, hey, like you do systemctl status with just the PYD, you can do it your own, and then it tells you, hey, like the PYD is running under this scope. And this is the unit that you would use. You can get that data out, and then you can decode it, and then you get the name of the unit, right? So it's pretty useful. You can use the manager to get the processes of the unit. And oh yes, because I'm not very smart here, it's not called session. This I have to use the actual scope, not the one on my tutorial. And there it is. And it kind of shows you like all the things that are running under that unit. And yes. So I think it's good time. We've been here for 1 hour. So another break? Cool. So this is going to be a little bit longer. We have it till 1 p.m., right? So this is going to be a little bit longer. Let's take 10 minutes. I think this was heavy enough for us to relax. I think there's still Portos and coffee. Okay, folks, 2 minutes, 2 minutes. Like a what? Sorry?
You go to the Ansible module,
Ansible
so
no.
for being able to control, like, find
Oh, okay. So let's do this so we can get to sandboxing. So we were on. Okay, cool. So now we can do some fun stuff, I think so. I think I need to. Okay, so let's hope this works. Okay, so we're going to go to a shell, to a terminal, and then we're going to hook to something that Anita did on her part of C groups, in which we're going to abuse the delegate option. Remember, Anita used that one to be able to delegate C groups, and that's how she was able to move bits around. We can do that programmatically. So let's take this, my first service. Let's add here delegates true. Right, and then I think this doesn't need a reload because that is not something that changes the state. And now what I'm gonna do is that I'm gonna call a systemd, actually, let's see if I can do this. Fun systemctl status, my first service. Yeah, so what I'm gonna do is that I'm gonna move this shell that is running, if you remember, is running as part of my scope, that is my shell. It's running there. I'm gonna move it to my first service, right? So I'm gonna do this, and wait, and if it works, you should see that it shows up here. So now first of all, it gets all the bells and whistles of like it's in a new C group. So if you have memory max or stuff like that, it kind of works. But it also now it's part of the life cycle of that unit. So if I were to do, like again, just to, you don't need to do it, but it shows you like, okay, now you're changed unit. Now, if I were to do something dumb, like terminate my first service, you will see that systemd saw that, oh, so the first unit, I have to stop it, so I'm going to stop everything that is under that unit, and my shell just went away. So that's something that, this is kind of like things that you can do. It's pretty cool. Now, so far, everything has been just basically Pythonify or make it systemd a little bit more Pythonic. This is something similar. So let's go back to our systemd shell. Sorry, where are you? Right. Oh yeah, so remember that there was a thing that it was called systemd run? Well, you can do the same thing with Python. You import systemd run, and then you can say something like systemd run infinity, right? And this is similarly now you're launching services in systemd that are ephemeral. So I'm gonna copy the unit, and then we can do unit. I think it's service, the main pid. Yes. And then you can see there is a main pid over there. And you can get the processes, and then you can get the ID. It's in unit. You can get the ID, and this is the name of the unit that you create, right? So if I go and do systemctl cat and do that name, you're going to see that it's a systemd transient unit created with API, exactly the same as you would create it with systemd run. Well, I did the status, but you already know that. Cat, you see it. But now we can do a little bit more fun stuff, right? So remember that with systemd run, we kind of start a shell, and then we can use that shell. So we can do this over here. And this kind of belongs a little bit, start being a little bit more Pythonic, in the sense that, oh, I execute something, and I was able to tie that unit to the std out of my current process. So now you can kind of execute stuff and start reading it. You can pass environmental variables, and you see everything that is going on there. You can also do the shell thingy, where you can paste this, and then this starts a shell, like systemctl status, and I'm a different shell. And now if I exit, I go back to my shell. That's also very useful. And here's where it actually starts getting a little bit useful, right? So we can use a thing that is called CPU quota. Oh, so basically you can add all the things that you want into this, and these are extras, are all the options that you would normally add into your systemd unit, right? So now you can build anything that you want. This one is doing a stress with one CPU, and it's doing that, and I think I can do htop. And there it is running, trying to do the stress of the CPU, right? I could probably do unit stop, and then replace. Yes, it's dead. All right, so now let's do this one over here, and let's see how we end up going. Okay, cool. So this one is trying to stress, and you see like it has two processes over there. This is what stress is doing, and each one is doing, it has almost none of the CPU that it can use. So each one is using 5% of the CPU kind of, and this is what CPU quota does, right? It says like for this unit, just use 10% of the CPU. Okay. There's a bunch of other options that are very interesting. Yeah, but yeah. The next thing that we can see is that this is, again, programmatically, we can use futures. And the idea of futures, it is, I build this, so if you do PP code, which is pre-defined code, CPU waste, I have a function over here, and this is just a function that all it's doing is wasting CPU, right? So that's all we wanted to do. We have an interface for PystemD that is called PystemD Futures. And what this is doing, it's doing kind of like, if you're familiar with what multiprocessing is, it's gonna run this function over here as a future, right? Like if you're ever familiar with the concurrent.future models in Python, it's basically saying, hey, why don't you run that function over there and here, because this is kind of cool, I think so. You're gonna run this function, but instead of running it on this process, you're gonna fork, start a systemd unit, establish all of these characteristics of the systemd unit, and then move that fork into that unit, and then run the functions there. Does that kind of make sense? So it's basically like this section of the code that I want to run it with a different C group. And I do this. And if I do here htop, you are going to see that there it goes. It is utilizing all the CPU there. So, but I'm running it, but you can see that I am kind of using just 10% of the CPU, while if I do it on here, which is CPU waste, I hope I don't kill my machine by calling this function. It's a 10. If I do it here, it's using 100% of the CPU, right? Because it can. So yeah, so this is like a good thing that you can use to just gate certain sections of your code. Now, of course, you can do something something a little bit more fun instead of doing that. So you can use a thing that is called transient unit pool executor. So instead of having just one section of your function going there, you can start a bunch of processes, put them in a different or the same C group, and then just schedule jobs and then make them work, right? So this is what this is doing. You schedule an executor, you set the attributes for the executor, you said I want 10, and then we can call and then see it like start submitting jobs, right? So I think this can run without anything else. Yes, so as you can see now it's starting, it's showing all the PYDs of all the processes, and it's using how much CPU they're using. As you can see, we have a limit, so so not all processes can use all CPU. This is not very cryptic, sorry, this is very cryptic, but the point is that we are running and scheduling jobs that are running on these machines, and they're all like sharing the same resources that are not the resources that are on my process, right, on the main process. Okay, so, and this is all happening in code, right? So you're sharing variables, you still have like all the APCs, you are forking, not execing, so that means that all the copy on write that you're doing, you get all that advantages. And I think that's interesting, and and I think we have been on this topic for way too long, and we have a notify and watchdog module at the end if we get to it, so this is not really relevant. We can do that later. So yeah, so this was the section, very long section, about how do you interact with systemd from a programmatic point of view. And now for something completely different but more fun, Anita's going to talk about sandboxing, aka containers, but not really. containerish. Oh, thank you.
Oh, sorry.
I was- It says that.
I noticed that was under your laptop, so you didn't see it.
It's not my fault. Let me see.
That's right.
Yeah, it looks good. May I ask you, if your screen is covered? Thank you.
Okay, hopefully everybody made it back to the table of contents and they found number 4, sandboxing. That's the one I'm going to go over today. So this chapter is styled very similar to the C groups one. We're going to go over how this technology roughly kind of works on the kernel without any systemd stuff. And then I'm going to show how, kind of the corresponding systemd property that relates to it. So the first topic we're going to talk about are mount namespaces or mount isolation. So namespacing is a kernel technology that allows you to kind of get like a feel for, allow you to like create more isolation with your processes and things. It's basically the backing for a lot of container technologies, if you've ever tried to figure out how those were implemented. Mount spaces in particular are related to making it so that the mount points in a file system appear isolated and basically inaccessible to other processes that are not in the same namespace as you. So in this first example, I provided a service unit called mount_ns.service with the following contents. So you'll see there's a lot of like protect home, protect system, private temp, bind paths. These are all systemd properties that make use of mount namespaces in varying ways. So for this portion of the workshop, I'm going to do like a tmux split like I did before. And on one side, we're going to just be in the Vagrant VM. And then on the other side, we're going to actually enter into the namespace that we're testing. So I am first going to So on the left side, I'm going to keep it as the, like this is the actual virtual machine. And then on the right side, I'm going to start running the systemd commands and use that to jump into the namespaces when I need to. So we're going to take this first mount ns unit and start it up. Nothing special yet. Because this unit is only run process, we can actually use systemctl show to print out the process ID, or we can use systemctl status if we want to. Here I'm using show. And we get that the process ID for mount ns is 1361 for my machine. So to actually enter into the namespace of a process, we're going to be using a Unix utility called nsenter. nsenter allows you to pass the process ID and also a list of namespaces for that process that you want to enter. In this case, we're going to be using --all, so just enter all of the namespaces for that process, and that will give us the same sandbox view that the process currently has. So I'm going to go ahead and copy this command, changing out these brackets with the process ID that I got earlier. So now we're in a shell inside of the namespace. So the first setting from the unit that we're going to take a look at is protect home. What protect home does is it sets the /home/root and /run user directories, basically all the user-based directories, to be empty and inaccessible in terms of like the view from the process. So we can actually check that by running ls on these directories. So you see that from the ns enter view, there's like nothing there. But if we run it from the actual virtual machine where we're not inside the namespace, that's the left side, you'll see that there are actually a bunch of other content there. So inside this process, you can't access it, but on the host, you can. I think the other interesting thing to look at is if you ls list the root directory, both inside and outside of the namespace, you'll notice the permissions are actually quite different as well. So on the left side, vagrant host, no namespaces. And then on the right side, from within the namespace, it's kind of ugly to look at. But if you look at like the home directory, inaccessible, no permissions here. On the left side, you'll see it has the standard directory permissions. Same with if we do like /run home and things like that as well. Any questions about protect home? Okay, so the next setting we're going to look at is protect system equals full. What this will actually do is mount over /user and also the bootloader directory /boot. Those will both be mounted as read-only. Because we're using full, we also set /etc as read-only, so from inside this process, you won't be able to write to those directories. There's also a strict property for protect system that mounts basically the entire file system as read-only, but we're only going to be doing this one today. So from inside the namespace and outside, we can try touching these various files. So like I said, let's clear this up first. I said the /user should be read-only, so we will not be able to do that from inside the namespace. But outside of the namespace, no problem. It's not read-only. And then we'll do the same thing with boot and also etc. And you'll see that boot and etc, no problem. We can run these just fine. Any questions about that? Okay. The next one we're going to look at is private temp. Basically, it mounts a new tempfs under /temp and /var/temp. So basically, same deal. From inside the namespace, you'll have a unique /temp to write things to, but outside of the namespace, you won't be able to. So we'll run the same experiment. We're going to touch this file, touch /temp. I named a file called Alvaro and Anita inside the namespace, and we'll be able to write it. The right side is inside the namespace, and if we ls, we'll be able to see it, that it is there. But if we try to ls the same thing, just going to copy and paste so I don't make any typos. You'll see that outside of the namespace, that file doesn't exist. You can't see it. So all of these properties by itself is pretty restrictive. So for example, what if you did want to create maybe a shared directory or a path that is shared between like the service inside of the namespace and also outside on the vagrant host. To do that, we actually use the bind paths property. There are actually a lot of different settings with bind paths, but we're just doing like the bare minimum where we set bind paths to /user lib systemd, which means it's just going to bind mount the /user lib systemd directory from the host, or in this case, the vagrant machine, into the namespace. So we can actually do that by attempting to touch a file under user lib systemd inside of the namespace. And we should be able to see from both inside and outside of the namespace that the file is there. Okay, any questions about that example? Yes? The question was, is there any detection mechanism you can use to see if you are within a namespace or not?
In theory, you can't, right? That's the whole point.
Well, yeah, I mean, the idea is that you can't, but obviously for the purposes of like the security holes and things, people have found ways to do it. I think one of the, I don't actually remember if I talk about user namespaces much here, but the user namespaces one is kind of easy to give away because the mapping between users and user IDs, something like that, is quite different between the host and within the namespace. For mount, I'm not quite sure.
Yeah, I don't know.
Yeah. I didn't really hear the question.
I guess what you are commenting is that maybe you can do it by inspecting what things you have available, like what directories are mounted or not. And yes, of course, like you could, in theory, reverse engineer this. And if you see your dev directory only have dev null, yeah, you probably are. Yeah, probably somebody's restricting you. But yeah, but that would be more of like a best effort kind of case. I don't know if you can, to be perfectly honest. Again, yeah, like the whole idea here is that it's supposed to be like transparent to the process, and the process shouldn't care. With that said, remember that security happens, and containers, and there's nothing more secure than your VM, or say like your machine, but then your VM, and then your container gets less secure. Sorry, in terms of escaping.
Okay, so the next thing we're going to look at is chroot, or change root. This is a way for you to change your root directory to be in a different part of your file system, basically. However, chroot by itself doesn't exactly provide an isolated resource like a mount file, like mount namespaces. All it does is change your view of where root is. Like you technically still have access to all the other files on your host. So basically changes you make in the chroot will still show up in the original directory on the host. We can give that a try with the chroot command right now. We're actually going to chroot into this directory called /opt debian. And we're going to cat the /etc os release file to see that because we changed the root to be this Debian file system that we provided as part of the image, it now looks like you're on a Debian machine. But remember, from outside of the chroot on the host, we are actually running Fedora machines. So now you have kind of two different OS views with you.
That was the thing, right? To show that you can touch, modify things in one and not affect the other.
Yeah, point. And I mentioned before that with chroot, if you touch the file from inside the chroot, let me clear this so we have more space. It shows up on the host, not in the same place. We are actually under /Debian, so we should be able to see the file from outside of the chroot on the hosts, like so, even though from the view inside the chroot, it's under /. Yep. Okay. So the thing about the chroot is that there are limitations to it. For example, procfs is not available. So if you try to cat slash the command line for PID1 from proc, it won't really work inside the chroot. So that is the right side. If we cat /proc/1/cmd line, it doesn't work. But obviously from outside of the chroot, works fine. Now we're going to see how systemd actually makes this whole thing functional. So for systemd, the property to basically do the chroot is called root directory. And that will mimic what we've been doing with the chroot command earlier. So we can take a look at the service I provided called chroot.service. And actually on the right side, I'm going to exit the chroot so that both of these are now back on the, back outside of the chroot. So this is the unit I provided, chroot.service. We're going to do the same thing we did, use root directory to make /opt/debian the view of the root directory. And then we're going to also use mount API VFS equals true, which will, let me double check, but it makes procfs and other features work by mounting it into the chroot. So that kind of fixes the problem we had before where we just used chroot and we're not able to use procfs. So let's go ahead and start chroot.service. For me, I'm going to start that on the right side. And same thing as before, we're going to get the main PID and ns-enter. This time I got smarter with my bash, so I'm just doing it all in one command. So that succeeded. We're now inside of the chroot service, all of the namespaces and whatnot. So if I try to, so now I'm able to touch files, and inside I'm actually able to view the proc1 cmd line that I couldn't before.
You can run apt. Remember? Everything
I can run apt, but I'm not going to.
What?
And then if we check from outside, we should see that the file we created is there just like we did in the previous example. Alvaro, Anita. Any questions about chroot? Hopefully that one made sense. And I'm going to exit the namespace. Okay, dynamic users. So we briefly took a look at dynamic users yesterday. And I think we also did a very brief introduction to the user property. So with the user property, you can change your unit to run as a different user. But that user has to exist on the system. The idea with dynamic user is that systemd will dynamically create the user on demand. When you ask for it, it'll give you like a random user ID, random username. And then when the service is stopped, it will destroy those users, clean it up like they never existed. So that way you're able to run your service as a user kind of like ephemerally. Like you don't need the system user to exist. Along with the user cleanup, it also cleans up all the files and state associated with the users. And this technology is done using mount namespaces. If you use dynamic user, it implies protect system strict and protect home read only. That's how it's able to do the cleanup so quickly. And there are probably, like, I'm missing probably a bunch of other features that it uses to privatize state as well. But just know that all this stuff gets cleaned up when your service is stopped. So I provided a super simple service called Dynamic User for you to try out. It only has dynamic user equals yes, and it's going to just run sleep. So if we start dynamic user, I'm going to start it on the right side. That's where I've been running units. And we can use the PS command to get the user ID of the running process by passing the PID in as an argument, and also a bunch of other things to list properties related to the process. So this is, bear in mind, this is from outside of the host, or outside of the unit. And you see that the username is dynamic something something. If you saw the whole thing, it's dynamic user. It tries to match the name of the unit, kind of. It's some arbitrary user ID. I didn't set any user ID in that service. If you can see more, it'll also show the C group and things like that. Okay. And if you cat /etc/password, which is where the system users are listed out, I know it's kind of hard to see, but trust me that the dynamic user is not there. So you might be wondering, if it's not in /etc/password, how does systemd actually get the login information or like the user details and stuff? Well, systemd provides a plugin called NSS systemd, which is like the name service switch library. So whenever you try to do like user queries, or in this case, we're going to use getEnt, we can actually look up the user on the fly. I'm just going to clear this. And you'll see that unlike /etc/password, we actually see the dynamic user details from NSS at the very bottom here. And if we go ahead and stop the dynamic user and run getEnt password again, the dynamic user disappears. Everything's cleaned up. Any questions about that? Yes?
You showed the cleanup out of, you say that's a password, but is the user's instantiation recorded in messages?
Oh, the question is the user instantiation recorded in like varlog messages or anywhere? Alvaro knows.
Yeah, it is. There is all goes into the journal, all this information. The thing that is important to know here is that why would we want to have like a dynamic user, right? So the common wisdom was that every time that you create your service, Postgres, whatever, you create a user, Postgres, whatever, to run the service, right? But you don't have that many users that you can create on your system, right? So if you want to take this idea and run every single service with a different user, you will run out very quickly. Dynamic users, what it allows you to do, it's basically for each different thing that you want to do, you create an ephemeral user, and then you delete it. The reason why this works is because that user cannot do many things, right? So the problem here is that if I have a user, I create a file, and then this file has the attributes of the user, right? If the user is gone, and somebody creates again different, like you overstep into those boundaries. This is why, like, also in Unix, it's very easy to create a user. It's very hard to delete it, right? So this is the other thing that it does. So yeah, so a lot of the problems that you face normal with users, like when it goes created, when it goes deleted, like you don't need to worry about. Should be on the journal, should appear. eventually, but I don't really know the command right now. If you ping us like after it, like I can give you. Yeah. We can't do it live. Go ahead.
Okay, so now we're getting into network isolation, which I think is the last namespace we're going to talk about today. Because at the very least, if your super bad process that you're trying to isolate gets loose on the host, at least you don't want it to get to the rest of your network and do some more harm. So we're going to talk about two different ways to do this. The first is private network equals true, which uses network namespaces. So what it does is set up a new network namespace for the process, and the only thing it configures is the loopback network. So for this example, we're just going to use systemd run to switch it up, probably because I was lazy. And we're going to use ns-enter once again to go into the namespace and examine the state of the system from within the process. Using systemd run, we're going to start a shell, connect to the sudo terminal, and then your shell actually automatically inherits the namespace. So we don't have to do like the madness with the ns-enter here. It just kind of happens. Let's go ahead and do that. I'm going to use systemd run to drop into a shell. And now we are actually inside a new network namespace. And we can use IP address to inspect that we only have loopback, whereas on the left side, outside of the namespace, we have eth0 visible to us as well. And you can further check that the network's not available by just doing a simple ping on both the host, and also you'll see that inside the namespace, network is unreachable. So the downside with private network is that it's all or nothing. Systemd actually provides more ways to further isolate your network at finer grain levels. So if you want to like poke holes to certain addresses, you can. And instead of using network namespaces to do that, it actually uses a technology called eBPF. So we're going to actually give that a try now. First, we're going to clear the left side, and on the right side, we need to exit the shell from the network namespace. Also clear that. And on the right side, we're going to run the systemd command. We're using IP address allow to only allow 8888. But we also do IP address deny 8800/8 to kind of limit the address space for our unit. So same as the previous example, we're using systemd run to drop into a shell inside of the service environment. And now if we run IP address again, you actually see that unlike before, we still have eth0, and on the left side in just the vagrant VM, it's pretty much the same. We have visibility on eth0, whereas before with private network, we only got the loopback. So now we can run some experiments. If we ping 8844, one of Google's other DNS servers, this should not work from within the namespace or within the service because we had denied that address. I'm going to clear this so we can see it better. Whereas outside of the unit on the left side, you can see that there's no packet loss. It worked. The right side, you see that once it timed out, 100% packet loss. However, 8888, this is the one that we allowed. This will work. So running this on both sides, 0% packet loss. Question?
Yes, will this still obey system firewall rules and like firewall internet tables?
I believe so. Those are they're kind of like additive. They're both kernel technology, so it's kind of additive. I think there are some cases. I'm actually not entirely sure what order they would run. BPF would. Yeah, BPF would take precedence because it ends up in the network stack eventually. If I didn't say the question was if we use like NF tables and other firewall rules, how would that interact with the technology, the BPF technologies?
Isn't IP table also implemented in BPF? Like XCV?
It depends on where you
Yeah,
put the
it
tables.
Okay.
These BPF programs will run on sockets in the input chain.
Yeah?
So if you have firewall rules in the pre-routing or those sorts of steps, that'll run first.
Okay, that definitely makes sense. So what I said, question to the void was, does IP tables, isn't IP tables also eBPF? And the gentleman here says, yeah, but it also depends on where you're running it. Like if you have a rule that is called on the, what did you call it, sorry?
Like pre-routing versus no
Yeah.
pre-routing.
So if you run something in pre-routing, we'll have different precedence on the other one. And it kind of makes sense, right? Oh, easy, sorry.
All right, so that's the end of sandboxing. Make sure you exit out of the namespace on the right side if you had one. Now I'm just going to go ahead and clear that and exit out of tmux, actually.
Okay, cool. Let's take 5 minutes.
All right, 5-minute break.
Okay, so
looks like it's okay.
We're almost done.
Oh, you want it a little louder?
Yeah, but that what Okay, everybody. First of all, congratulations for staying so long. This has been a long day. We really appreciate you being here, and I hope this has been useful. We are heading up into our last half an hour, where we're going to talk about the last two topics that we kind of plan to talk. And if we have more time, we will like squeeze everything else that is outside of it. Keep in mind that this is just like a brush into the world of systemd. There's way more to do it. This could literally be a whole conference. It's about just systemd, and we will still have things to discuss because it just touches like everything inside of the kernel technology. So what we're going to do now is that we're going to talk about Notify and Watchdog. And this kind of falls into the idea of systemd for developers, because it is still a little bit on the part of like, how does your program interact with systemd in a way that it's more complementary with each other, right? So we have been seeing a lot of like Notify units. And these are the type of the unit where it's not simple or exec or anything, it's just say Notify. And so far, the only thing that we have kind of like figured it out is that the Notify unit is a unit that tells systemd when it's ready, right? So, when you set a type of Notify, however, like it's very similar to when you do exec. However, it is expected that the service send a ready equals 1 notification message via not a call or equivalent to tell systemd that something has gone. So let's inspect the first unit that we have here for you. It's called basic notify not. That is, if you just cut it, you will see that it's something like this. It has a type notify, and it's executing a script. One noti, which I can spell, so I put one notify instead of like one notify. So if we do cut this one, you're seeing that this is very simple. It's a Python script that it's just sleeping for 3 seconds, 3.5 seconds. And if you see here, and you see the unit, it says that is notify, and it says like you're allowed to only take 3 seconds to start. Right? So if the theory here is correct, this unit will start the script. The script will try to sleep for 3.5 seconds, but systemd should kill it at the second 3 because it didn't reply and said, hey, I start. So let's do this. And then you're going to see something that you haven't seen yet. That is the shell just hang, which is something that hasn't been very common in our workshop, right? So you execute a command, it returns. So what's happening here is that the unit didn't, whoa. The unit didn't start if I, if I do status, you're going to see that it fails, and it says, start operation timeout terminated. Failure will result timeout. So this is what happened. Now, if we go and this is all the same that we were saying, operation terminated with timeout. So now if you go and try this other unit over here, which says basic notify yes, and you start it returns right away. So what's the difference between these two things? You can cut it, and then you can see that this one is way simpler. Let's do so it's way simpler. It's just send a message to systemd saying, hey, like, get ready, like, I'm ready. So then the application still sleeps for 3 seconds, right? And I can do, like, it can sleep for whatever amount of seconds I want, like 3.5. Same as the other one. And it will still tells you, like, hey, it's activated, right? So that's the main difference between these two, that you send a message here. But now that we are sending message to systemd, we can probably send other messages to systemd to make our life better, right? Pay no attention to this false at the beginning. We will explain it later. But here we say ready equals 1. If you go into the documentation for systemd notify, you are going to see that the message that is sent, it's ready equals 1, but in capital ones, right? So the library under the hood does this, and no, there's no need to worry about it. You can add it a lowercase, uppercase, doesn't really matter. Okay. Okay, so this works, and when we do status of the service, we see that the start, and then it's marked first as starting, then at started, then it outputs the output, and then it deactivates correctly. So it does exactly what it's supposed to do. All right, so as I mentioned, the magic is here, and as always in this lab, we are going to try to do a couple of things that gets better when you have a Tmax broke screen. So we are going to execute a shell. Let me execute the watch in the bottom, and then I am going to execute here this shell. So I'm executing this shell over here, and then you see that is, I should probably show. I'm starting the unit, and I'm saying that the service type is going to be notify. So I give it a name for the unit, so I can kind of trust it here, and then I can do reset, systemctl reset failed. Yeah, all right. So that's what it is. So I start the unit, it's a notify unit, and it says activating, but it hasn't activated. So if I go here, now I need to go and paste, sorry, there you go. And when I do ready equals 1, it changes the the status to active, and it says when it was active. So this is how, like, you do this. But we can also, like, set a simple message status, right? So we don't need to send, we can send multiple messages at a certain time, but we can say something like status, and And then you are gonna see that now it show up here. And it's right there, right? So you can use this to communicate information. You don't have much part there, but yeah. Now, if for instance, you have, like if you want to reload and you have something like a socket unit where systemd is handling the connections and you want systemd to hold stuff, or you want to tell systemd, hey, I'm reloading, so like acts according to it, you can actually send information, hey, I'm gonna be reloading. And if you see now the status of the unit is reloading, right? So imagine that somebody sends a zip hub to you, you can tell systemd, hey, I'm reloading, and then systemd can hold a lot of, like again, when you have sockets, it will hold the connections, it will not send it to you because your unit is not healthy. And also there is timeouts that will take take place if you don't reload on time. Then, for instance, we can do something like status and ready equals 1, and I'm going to change the status to this is new. And then you set both of them at the same time, and that's just great. Now, there are other things that you can set, like the error number, and you can see that now there is an error message there. Right? I mean, that error number can be anything. 42, I think it's just no, that's the description of that error, no message of desired type, but you can do 43, and then it will show you a different message. And then you can do the exit status, which is just a text that you can consume at the other end, because this is now part of the unit, but systemd does nothing with this information. So far, any questions? Go ahead.
For the base notifying not service, did that one fail primarily because the timeout was, it took longer than 3 seconds for the job to start?
Yes, and to finish. Yes, that is true. Yes. Yeah, so but it doesn't took, yes, so let me put it like this. It took more than 3 seconds for the service to start, but the definition of start, it is when the service sends the ready equals 1 to systemd, right? So the application started, it was doing stuff, it printed something. It just, and it was sleeping, but it didn't send the ready equals 1. Once you send the ready equals 1, your service is starting, is started, and now a whole new set of rules start applying. And this is relevant for watch, though, that we're going to see later. But yeah. There you go. So those are relatively good ideas. Right. So you can inspect the systemd notify. The SD notify man page, and then you'll see all the messages that systemd can accept and what it's doing with it and why is it using. Now, with that said, what happened here when I write foo equals true, right? Clearly, like systemd doesn't have a foo thing implemented. Systemd just ignore every single message that goes there and it's not part of the allowed messages. Now, you may ask yourself, how is this implemented? Like, anybody has any guess on how this would be implemented? That was everybody's idea, but no, it wasn't divas. But yeah, most people thought it could be divas. So it's very simple because you want applications to be able to do this without having to bind to a very weird library, right? So you wanted to do it on the most possibly Linux native way. So it is implemented with sockets. So if you do import OS and then do environ, you will see that here there is a notify socket, right? And that socket is an UDP socket that you just send communications to, like send messages. And the messages are clear text message separated by a carriage return. And that's kind of it. Now the permissions on the socket are based on the user. So this is systemd. But if I were to do, it's not part of the demo, but why not? if I were to do systemd run unit type notify and then do env, but I want to access the user bus, something, it wasn't unit type, it was service type? Service type. Bash, I believe. What? Oh, sorry. Oh yeah, so if I do M here, you will see that yeah, you see that the socket that is passed to the unit is a user socket. Now this is from the user, right? So inside the machine, I'm root, so I get access to the root socket. For each user systemd will mount a socket there. And that's how you manage permission that so different users don't step each other. Okay, go away. Okay, so moving on with that, there are some messages that you can send that are catastrophic. So the first one is this one. Yeah. So the first one is this one, where I swap the true for the false for a true. So what happened here is that systemd it's every time that you send a message, systemd keep the socket open for you, right? But if I send true, you're actually saying systemd close the socket. I will not send you any more messages, right? So the idea here is that if you're only using notify to start your service, once you start, you just say like, don't listen to me anymore. And I do this, and now it is great, if I'm not mistaken. Okay, and now we say, we can send like a message, and this is get ignored, and then you get a status 0, saying that, hey, like the socket it wasn't allowed. So we close it. Okay. The other message that you can send that is also now you're basically like a dead sentence is that you can send the stopping equals 1. So this is telling systemd that you're gonna start stopping. So you do this, and then systemd has the status. Oh wait, sorry. Active, and now we can do stopping. Oh, I am not on my best game here, so I can do false here. Then ready. And well, so by the way, that's why the true is happening, right? To avoid that somebody just issuing a stopping after you do your ready. If I do stopping, it changes this to deactivating, and then systemd will send the stick term that it's supposed to send, and then we'll wait for the process to exit correctly. There's no coming back from this, so you just need to exit, or systemd will eventually like kill you. Okay, so with this, we can actually do a couple of other things that are kind of like interesting. So one thing that we can do is that we can start process, right? So for instance, I will start a sub process over here that is sleeping, and I'm gonna make it sleep for 10 seconds, so we don't wait that much. So if I start this process, you're gonna see it is right there, right? But now I can do something. I'm actually gonna do it with a new one. So I'm starting a second sleep, and then I'm gonna change this to say main pid equals p pid. Wait a second. I actually want to do the 30 seconds. So I'm gonna send the main PID equal PID. And here you see that the main PID is this one, 1852. I changed the PID, and then it changed to the main PID is now 1924. Right? And now if I exit, you're going to see that system D is there waiting for the PID to go away. That's sleep. And yeah, it 30 seconds passed, and then it's gone.
Is that called an exec?
Sorry?
Is that called an exec in a way?
Yeah. You're asking if that
Is that what that was?
yes, that exit, yes. So he's asking if that was exit, and the answer is yes, right? So now we enter into an area where, like, who actually can send these messages, right? So, and the answer is very simple. So we have a very simple batch script here that you can read, that all it does, it sends a notify message with a shell command, right, using systemd notify. Now, if I do systemctl start the batch, you're going to see that it returns right away. And then if I do the status, it exits correctly, like it was deactivated successfully and everything. So if you know anything about like how processes work, systemd will start this shell script, and this shell script starts as a batch script, right? So then this batch script will execute systemd analyze, but systemd analyze is a binary, so it's its own process. So it has their own PYD. So this systemd analyze, it's going to be the one that sends the message. So systemd right now is trusting any process that is under the hood. That's my theory, right? So if you, because systemd notify should be a different process than the main process. And that's kind of like the theory. But in practice, this is not true, because if I try to start this one over here, you see that it hung. So it's clearly not doing that. And if I do cat, it's exactly the same shell script. The only difference is that I'm using user nobody, while in the previous one, I'm doing it as root. So what is happening here is that systemd notify is impersonating the PID of the main process. So systemd only trusts the main process to send requests. But if you're root, any process under your tree can impersonate. But if you're running a thing like as nobody, systemd analyze cannot impersonate the main PID. Did that make sense to people? Okay, perfect. I know it's weird and it's hard to modify. So the way that you get around this is that you go and then you change this option over here for the notify, right? And then let me show you here, you just ask for the user, you add the notify access to all, and this will tell systemd start trusting everything that is under the hood. So let's start this. Again, it's exactly the same service as before. And you see that it returns right away. And if I do status, sorry, this is me pasting all that crap, broke everything. So. And now if I do start, and then if I do status, you see that it's waiting because it's doing the thing, but it already has the status active. So it allowed, it passed the notify stage. And that's it with notify. The last thing that we want to see is watchdog. So watchdog, it's pretty simple. So if we have demos that just execute this shell over here, and we're going to set an option that is called watchdog 3 seconds. What this is doing is the following. Your application, the same way that you have to send a ready equals 1 to signal that you start, you have to send watchdog equals 1 every 3 seconds, or at most every 3 seconds. So if your application doesn't send watchdogs equal 1 in the notify bus in this timeout, systemd will decide that your application is dead and it needs to be restarted, or apply any technology there, right? So if we start this one, and then we do status, you're gonna see that it actually executed. It's actually executed and it finished completely. And if we go and check that script that we were talking about, we could actually just check it here. I think it's gonna be better. There you go. So this is very simple. We send, this is a notify service, so we have to send a ready equals 1. And before you send this ready equals 1, your system is starting, so you don't have to send any watchdog message. But after this, you have to set watchdog messages. So with watchdog enabled, you get the timeout that you need to do, and then you can send messages accordingly, right? So I get the nanoseconds that are there, and then I can wait, I can sleep for a bit, that as long as it's not the time that's going to do timeout, I send watchdog, and then we are okay. The next one that you can do is that we can look at the second example, which just use, it's exactly the same, but the script is different, right? So the script is kind of to show that I get the seconds, but I'm going to wait for 10 more seconds on the watchdog. So if I do start the second and then do status, you're going to see that it's active, and then it failed. And then it says, hey, it fails with watchdog timeout, and it sent a SIG abort, and the main process just exits with SIG abort. So that's it. But now you see that it sends you a SIG abort. Now, if you see the third example that we have here, maybe we can also look at it here. It's maybe be a little bit better. You're going to see that now we can send in the dbus, sorry, in the notify, we said watchdog equals 1, but we can also change this timeout, right? So imagine your application has started, and it has a while start. It needs periodic sync, so you will send this, but once it started, there's a little chance that it will fail. So maybe you want to decrease that time. You can do that at runtime, and you change it here. Just beware that are microseconds. So in this case, I'm adding an extra microsecond, sorry, an extra second to the timeout. So in theory, what I'm doing here is that I am going to send a watchdog, and then I'm going to sleep for 1 second less than the watch time. So it should like finish successfully. And I know these are very artificial examples, but I think it's the best way to kind of display what this is doing. So, and it finished, and it's clearly successful because it doesn't tell you that it's an error. So it sleep for the watchdog time, but since we changed the watchdog to be 1 second more, we still have 1 second to spare, and we exit successfully. So yay. Oh, we have one more one, which is this one. So here, cut, you have the W5, and there's a mysterious 4 that is the missing link. This one in particular, this one is actually quite cool. What this one does, and I remember why you have the other. What this one does in particular, it tells systemd to trigger a watchdog. So inside your application, you decided that you're not healthy. Like, what do? like, instead of like you yourself taking that decision, you can tell systemd, hey, like, I cannot send you a watchdog anymore, so can you please just kill me? And remember that I told you that this thing takes a send a sig abort? So what I'm gonna do is that I'm gonna capture that signal, and then I'm gonna print something and then exit successfully, right? Like I'm not gonna exit with an error. So we start demo 5. So if this is true, then I can do, and then you can see that it started, and then somebody requested the watchdog, so the process kill was finished. But if you see, even though the unit failed with watchdog status, the exit status of the unit is 0, which was the one that we did. So this is how you do it. And the final, and we're gonna just finish running time, it's this one, which is called watchdog and set. And what it's doing, it is what if you don't want to be watchdog anymore? So just look at this one. I'm just gonna start. And then I'm just gonna do status. And then this, whatever it's doing, is not dying, so if I see watchdog and set, all this is doing is setting the watchdog U seconds to 0, right? So that's a way that you tell systemd, I don't really want to be watchdog anymore. And with that, ladies and gentlemen, we reach the end of the scheduled programming. So again, thank you very much for coming. I need to ask this, did anybody learn something new here? Then we did our job. Want to say something? All right. Thank you very much and enjoy the conference.